My name is Charles Jiao, and I am responsible for ICA electrochemistry products. Um, Thank you everyone for spending time with me. And in this lecture, I wish to take you to the journey of how ICA illuminates the renaissance of organic synthesis. So as I am sitting here with you guys on behalf of ICA, we are not pretending that we invented something because the truth is that electrosynthesis has been an ancient technique invented back to the 1800s by scientists. And since then, we are able to trigger a lot of reactivities, such as a CC bond formation here, or a CO bond formation here, or CN bond formation, and so on. Starting from 2017, that has been the age of electrosync, which is our major topic today. But before we move on to the product, I wish to briefly summarize the mechanism of electrosynthesis. When we are running electrosynthesis, we are combining organic synthesis with electrochemistry because with organic chemistry, with organic reactions, we involve redox reactions. And what else has redox reaction? Electrolysis. And that is why for electrosynthesis, we require the same components as electrolysis. Here we have a power supply, we have wires, we have a pair of electrodes, and we have conductive solution that also contains um, the substrate. Once we turn on the electricity, in the solid phase, we are pulling electrons away from anode and we are pushing them to cathode. This is how we establish the potential difference. And in the conductive solution, because of the potential difference, charged species and reagents move in the liquid phase accordingly. But in order to close the circuit, there is one missing part, which is between liquid and solid phase. And that is where redox reactions take place. So here on the surface of anode, oxidation takes place, and on the surface of cathode, reduction takes place. And combining all those factors I have mentioned, we are able to finish the circuit. And with electricity going through, we can run synthetic organic reaction. So that is the mechanism of electrosynthesis. And how do we substantialize the concept? What does the setup look like? So traditionally, this is what your reaction looks like. You have a lot of equipment, and let's focus on the chemistry part in this test tube. The resolution is not very clear, so let's simplify the concept and bring it into a diagram. So for electrochemical cell, uh, typically it's made of glass for visibility, or you can also use plastic for some very aggressive solution. We have a stir bar underneath to make sure the solution is homogeneous. And as for the solution, it has solvent, of course. It also contains substrate, and we also need electrolyte to make sure it's conductive. And then we need electrodes. We need a pair of electrodes for sure. And for some type of reactions, we may need reference electrode. I will introduce in which scenario we are going to use reference electrode later. But moving on to the next part, we also have a cap for electrochemical cell to make sure it's a closed system when it's necessary. And on top of the cap, we have septum. This is designed for the addition of reagents or solvent, or you can insert an argon balloon through the septum. After assembling the electrochemical cell, you can put hook a pair of alligator clamp uh, to the potential state. And from the potential state, it provides different type of power supply, which is also the reaction mode. So the most common reaction mode is constant current, where you define a certain current value. Current represents the rate of electron movement, and by defining a certain rate within a certain period of time, we can make sure how much electron was passing through the reaction system. So as long as there is some reaction happening, we can make sure of the chemical conversion. And that is why constant current is the most common reaction mode. Alternatively, we also have another reaction mode, which is constant voltage, where you define a certain voltage value. In this case, we are interested in the desired reaction voltage, meaning that it's either oxidative voltage or reductive voltage. So the voltage has to be absolute, and we need an absolute reference point to make sure we are able to control the voltage very precisely. And this is when a reference electrode is required. The reason we have constant voltage reaction mode is that for some reactions, it has a lot of side reactions whose reaction voltages are very close. So by choosing a constant voltage, you are dialing into a specific reactivity so that you are able to improve your reaction selectivity. So that is the cell component and power supply, aka reaction mode. And you may have noticed that I am using undivided cell as a demonstration. So I want to introduce another cell type, which is very intuitive, divided cell. Um, Most of the components are the same, and the only difference is that for divided cell, we have a freight or permeable membrane between the reaction chambers, between the oxidation and reduction reaction chambers. So traditionally, divided cell reactions are carried out in an H cell, and this is in the middle, indicated by the arrow. This is where you put the membrane in between the reaction chambers. The reason we put the freight or membrane is to separate the solution, and most commonly, separating solution is a great way to protect your desired product. For example, if you run a reaction and you want to protect your desired oxidation product by choosing the membrane, you are able to trap the oxidation product in its own reaction chamber so that it won't be counterparted in the cathodic reaction chamber. So far we have covered the mechanism of electrosynthesis, cell components, cell type, and reaction mode. Because of the strong catalytical power of electricity, people are able to discover a lot of unique reactivities that has been inaccessible in the past. And that is the first advantage of electrosynthesis. Due to the strong catalytical power, we are also able to circumvent dangerous or toxic materials or expensive reagents. That's how electrochemistry contributes to green chemistry, how we are able to improve the sustainability, and that is the second advantage. Thirdly, for the same reason, electrochemistry is so strong that we don't have to use toxic reagents, and we are able to avoid the strong reaction phenomena such as flame or even explosion. Everything can be done electrochemically. So that's how EChem contributes to safety. So combining noble reactivity, sustainability, and safety, electrochemistry has greatly helped chemists when they are in desperation. But here comes the question. Since echem is so great, why people turn to electrochemical approach only when they are in desperation? Given all those advantages of electrosynthesis, why it wasn't the mainstream for a long time? And that involves some engineering challenge. So looking back at this picture, in order to set up your reaction, we already know every chemistry is within this small test tube, but you need to put up with a slow laptop because you don't want to spend too much money on a computer that is only used in a lab, but you still need to buy one. And you need to download the software, you need to put up with the um, license and maintenance, and then you need to buy a potential stat. You finish all the connections and tolerate with the fragile, customized alligator clamp um, type of connection. And then you buy a ICA stir plate and put underneath the reaction. So that is a long purchasing list. You you shop everywhere, and then you go back to the lab. So looking at this setup, nobody wants to do electrochemistry for sure, and that's the major reason it wasn't the mainstream. And what if we have the computer inside a stir plate? What if we also have the potential stat inside a stir plate? Everything will be easier, and that's the vision of Mr. Rene Stiegelmann, the owner of ICA. So visioning the gap between chemistry community and engineering application, we look at us, ICA, and we realized that we were actually the first manufacturer of potential stat back to 1950s. So we are very proud to say that EChem is in our DNA. And with that confidence and experience, ICA partnered with Professor Phil Barron from the left. Um, Professor Barron is at the Scripps Research Institute, and we started our collaboration with the chemists. We opened an R&D office next to the Scripps Research Institute, and we have carried out the engineering design, and also everything was field tested in the chemistry lab. So in 2017, we released ElectroSync, a three-in-one instrument that allows you to run the reaction, helps you to take a quick CV, and you can use it as a room temperature stir plate. So for the next part, let's come to the exciting part, ElectroSync, and I will break it down function by function, starting with running the reaction. So from the previous slides, we have already known that electrochemistry was very complicated to set up due to the equipment. And now electricity has the concept to put everything within a hand-large size equipment. And what is more impressive is that in addition to the traditional reaction mode, we also provide you smart assist for beginners. So all you need to do is to load your chemicals, identify the polarity, and then install your electrodes accordingly. Then go to assist mode, telling the device how large your reaction scale is. Take some suggestions of choosing electrolyte and solvent, and then define your power level of your reaction. Then the instrument will analyze the solution, suggest you with a starting constant current value, and then you run your reaction. So with electricity, everyone is able to run the very first reaction in their whole life. And after running the first reaction, of course, um, you need to run an MR and see how much reaction, isolate your desired product, and see how much yield you will have, and then you optimize your reaction. So from your second experiment, you need to be familiar with the reaction settings. And on electrosync, it also inherits the traditional reaction modes. You need to set up your constant current value or constant voltage value alternatively. You will decide whether you are going to use reference electrode, and then you define your reaction duration. You can always run it continuously, but in order to run the reaction in a certain period of time, you either define by time, or you define by the total amount of electron injected into the system. And then in the settings, in the parameter settings, you will also need to decide whether you are going to alternate the polarity. So most of the parameters are very obvious. And for the next part, I want to dive into alternating polarity with more details. Why do we need that, and how does it work? So alternating polarity is recommended to circumvent fouling, deposition, or corrosion. So let's take an example of deposition. If you are using a pair of platinum electrodes, and within a short period of time, you will form some deposit on the surface. This hampers the proceeding of your reaction. And how do we keep the surface relatively clean? How do we keep using the surface property? Alternating polarity. So what if the electrodes physically remain the same, but function-wise, they are flipped? The electrode on the right-hand side will be anode, and it will run oxidation reaction. So let's continue playing. Now we are able to get rid of the deposit. Problem is, we form the deposit again on the newly become uh, cathode. And how do we get rid of this deposit? You have the idea. We just periodically switch the polarity and keep getting rid of the newly formed deposit from the electrode surface. And that is a trick to keep the electrode surface property. When corrosion happens, it employs the similar philosophy. So this time, instead of getting rid of the deposit, it's more of having both electrodes take part to be consumed, so that we are able to make the reaction longer. Because we consume the electrodes more slowly. One note when you're using alternating polarity is that you have to choose a pair of same electrodes. Because otherwise, for example, if you're using graphite and platinum, every time the polarity switch, anode and the cathode will be different, and thus you lose the consistency of your reaction. So yeah, that's about alternating polarity. And by far, I think we should be all aware of the meaning of each setting, and then we can run the reaction and keep optimizing it. And that's about the first functionality, the reaction mode. For the second functionality, CV, that represents cyclic voltammetry. We have all learned cyclic voltammetry in classes, but we barely have had experience as organic chemists. We barely have experience with CV. For the same reason, the settings is too complicated, and it wasn't practical for us. But with electrosync, I guarantee you this is the easiest CV you can ever run. So very similarly, you assemble your electrodes by identifying the positioning, and you load all the chemicals in the glass vial, and then you put it on the instrument. You go to CV mode. You either use the default parameters or you define your own parameters, and then CV is plotted on the screen. So as I said, electrocene is organic chemists' favorite CV tool, and there are a lot of papers, publications using electrocene to measure the CV. With the help of CV, you can generate uh, the duck head shape curve, and you will understand uh, the redox peak. Uh, you have further understanding about at what voltage the reaction will take place, so that coming back to the synthetic point of view, it helps you to understand your product with more insight, and you can also use constant voltage to dial into the specific redox reaction you are interested in. But since we have talked about publication, you want to show the world how you uh, get here, how you approach to this um, property of the chemicals, electrochemical property. So how do we export the reaction data? The first method, you can always use a USB flash drive to export the data. The USB flash drive comes with the CV electrodes, and it can be inserted behind electrocene the device, and then you can finish your data transfer. And alternatively, you can also download electrocene app on your mobile device, and then you can uh, the app synchronizes the CB result, and this is how the curve plots on your cell phone. And once CV plotting is finished, you want to tap on the camera icon. You will send your data either as image or CSV file through email as an email attachment. You can send it to yourself as a backup. You can send it to your boss as a report, or you can even share with your family and tell them how much you love electricity. So that's our second functionality, CV. In addition to the three different functionalities, we are also thriving to provide you great service and support. So we wish to evolve for chemistry in addition to all the warranties we have for you. Because nowadays, all the devices are smart, and so is electricity. Everyone is using the app, and we wish you do the same with electricity. And we are building a community for electrochemistry so that scientists are able to communicate with each other more efficiently as what we are doing here right now in this lecture. But for as for today's lecture, I want to focus on the smart device part by introducing a very useful newly invented reaction mode, RAP, which is a new solution to chemoselectivity, and it can be achieved by updating your software. And here is how the story began. Dr. Kawamata from the Baron Lab, he pointed out that for many substrates, they have a lot of redox active labile circled in red. But the desired reaction, the desired redox labile might just be one single spot, as indicated in the green circle. How can we achieve the desired product without triggering other side reactions? With the traditional waveform, the direct current, um, it's not very possible because um, you cannot, you just simply cannot avoid all those side reactions. And at that point, Dr. Kawamata pointed out that um, between the between the initiation of the undesired reaction and the happening of desired reaction, there is such an interval. So if we switch the polarity fast enough, we are able to catch that interval and avoid the happening of undesired reaction in theory. But practically speaking, that interval is so small that the traditional alternating polarity won't even satisfy uh, this demand. So we have to invent something new. We have to invent a new reaction mode with a faster or say more rapid alternating polarity. And here is our rep waveform. With rep, you have um, you have a higher frequency to alternate the polarity so that you are able to catch that very small interval. And this cannot be single-handedly done by chemists. And that's why I want to introduce our engineer, Mr. Xiaobing Shaji. Uh, he invented the new software version that enables um, the device to run the brand new electrochemistry reaction mode, REP. So the update can be available free of charge. All you need to do is to go to the website, and we have an update tool for every electrocene. Uh, each device is able to evolve uh, into this version, giving you higher selectivity for your reaction. So with standardized platform with evolving device and software, electrochemistry has been um, growing very vastly in the past few years, and electricity was has been a major contribution in the publications. There are a lot of reactions invented by electricity. All those papers are able to be repeated, and you can experience a very reliable reproducibility due to the standardized platform, especially the electrode. And that brings us to one last piece of reproducibility, how to choose the electrodes. So from our side, we offer you the most common electrodes with standardized dimension. And in addition to that, we want to give you a very introductory suggestion for how to choose your electrodes in case you want to invent some reactions based on what we have discovered in the community. So if your desired reaction is oxidation, you want to use non-sacrificial anodes such as platinum or other carbon-based materials. We have, for the material of platinum, we have platinum foil, which is more durable in very harsh conditions. And we also have platinum plated on ceramic. This is a mid-ground solution um, considering the affordability and a milder reaction condition. And as for carbon-based materials, we have RVC, uh, a foamy carbon electrode, which gives you more surface area and thus improve the electron efficiency. We also have graphite, which is a starting point for everybody. And we also have more pure carbon electrode, such as glossy carbon and boron doped diamond. But what if oxidation is not desired? In another word, your desired reaction is reduction. In this case, oxidation will happen no matter what. But in this case, we want the electrode to be oxidized rather than the organic material. That is why we have sacrificial anodes such as magnesium, zinc, aluminum, and stainless steel for the undesired oxidations. And this is the selection of anode. And as for the selection of cathode, Here are some typical materials such as magnesium, zinc, nickel foam, RBC, and other carbon-based materials. For nickel material, we have nickel foam as mentioned. This has higher surface area, which improves the electron efficiency, but we also have nickel metal um, as another type of electrode. So in order to find all those electrode information and any other materials that are not covered but still useful, you can find it on our website. And everything I have mentioned about choosing electrode um, for desired oxidation or desired reduction can be found in this beginner guide, and it also gives you suggestions for choosing solvent and electrolyte. So as mentioned, there are a lot of papers published with electricity, and here I wish to show you more case studies. Um, So the first reaction is decarboxylative arylation. This paper was recently accepted by JAX. And in this paper, the Barron Lab, in collaboration with BMS, Biogen, and Pfizer, they discover a unique access to the decarboxylative arylation, which cannot be accessible with other means. And the reaction is air friendly, requires and it needs just technical grade solvent and reagent, very cheap and accessible nickel source catalysts, and also silver nitrate. And the reactions can be done under room temperature. And using the proposed mechanism, uh, you are able to synthesize uh, intermediate towards Rapaflo, for example, which is very useful for medicinal chemistry. And the second paper, doubly decarboxylative coupling, delivers a very similar message. So from the Barron Lab, in collaboration with BMS, they have discovered a unique access to this CC bond formation, starting with acid activation without no solvent exchange in one single pot and catalyzed by nickel and electricity. And with the help of electricity, they are able to reduce the step count very significantly. So here are some selected results. And in addition, they have also proved the uniqueness of this method. They are able to achieve very high yield, which in comparison, other means gives you trace amount of product. In addition to noble reactivities, electrochemistry has also reinvented a lot of previously challenging conditions. So, for example, aryl amination, um, as an example, this was in collaboration with Pfizer. By using electrochemistry, they are able to access to a broader scope of the synthesis, and the reaction is also more stable in order to make useful medicinal chemistry materials. Besides the scientists from academia and the collaborators, our customers from Novartis have also tried these conditions, and they have found electrochemistry very useful for their discovery. Here, I want to give you some additional recommendation to for reading. Very similarly, for um, CO bond formation, this paper was collaborated with BMS. With electrochemistry, you are also able to increase the reaction scope and also increase the reaction stability. So another example here, how electrochemistry improves the reactivity can be illustrated by CSP3, CSP2 coupling uh, from the Savolve lab. So what they have discovered is that depends on the complexity of the molecule. Some of the cross electrophile coupling is very accessible with electrochemistry, but with a more complicated structure, um, the accessibility is far less known, even with electrochemistry. And what the Savolve lab did in this paper is that they discovered a very unique path to catalyze the reaction. They find a very interesting way to access to nickel zero so that they are able to catalyze many challenging reactions with complicated molecule structures. And here are some selected results of this paper. One last paper I wish to show you is the CSP3H oxidation. And this overall, this paper is a late stage methylation, but electrochemistry, anodic oxidation plays an important part presented by the Lin Lab in collaboration with Genentech. So they have made significant improvement based on Shono oxidation, and here are some selected results. And the Lin Lab also proved that this method can help the methylation can help medicinal chemists synthesize some useful medical compound. So here are the 5 most important papers for synthetic chemistry, for medicinal chemistry that you should not miss. And at the end of the day, after the discovery, we want to put it to a larger scale. We want to put it to a commercial uh, manufacturing scale. And this has also been proved effectively. And here, the picture on the left top corner is the O areolation I mentioned earlier. And the paper on the right-hand side is the amination paper I mentioned altogether. They both uh, increased the reaction scope and increased the reaction stability. The paper on the left bottom corner is birch reduction, but it's done very safely and discovered on a smaller scale and then proved effective to be scaled up in a gram scale. Electrochemistry has also drawn a lot of interest from industry and process departments in many biopharm companies have designed uh, larger reactor to scale up the reaction. Here is one example by Merck. So at this moment, if you recall, electrocyn is 3 in 1. I keep saying electrocyn is 3 in 1, but we only cover reaction and cyclic voltammetry. There is one missing part, and I did it on purpose. So the last one is a room temperature stir plate. You simply take off the single vial attachment and you put the stir plate accessory attachment on the device. This attachment comes with every electrocyn package. And then once you install the accessory, once you see the screen changed after the installation, it functions as a room temperature stir plate. Initially, we had this idea so that at, so that in case electrochemistry doesn't work out for you, it can still serve you 24 hours a day, but it's never the case. But the valuable information is that the concept of modularity really inspires us with further product development because as we have promised you in the past, there's only one type of electricity instrument and all those additional uh, all those new reaction mode can be implemented by the free software update. So what if you have some requirement or demand that has to be done on the instrument, on the hardware, given electricity uh, will never be obsolete. Accessories. Just like how we install the stir plate module, we modularize other accessories in order to provide you additional functionalities so that you can run your reaction more efficiently. So we have accessories that extends the power of electricity so that you can run your reaction in a heat bath, for example. And we have even smaller scale reaction, but it's equally powerful. You can run and monitor multiple reactions on a carousel, and we provide some accessory that improves the sealing so that you can say bye to glove box. And we create the division in electrochemical cell. And finally, you can run the high throughput reaction uh, in something similar to a honeycomb. So all those messages, all those concepts, all those functionalities are available on our accessory page. And because we have a limit time, uh, I will be available answering the accessory questions in the FAQ session, and so do my colleagues. Also, we are always awaiting for your inquiries at any point in the future. But as for today's lecture, that will be everything I wish to share with you, and I hope you enjoy my talk. I also wish you a wonderful journey in electrochemistry. Thank you.